In this class, we're going to have a look at the concept of continuity. You have seen this concept before, and in fact the concept itself is not different from what you have learned before, unlike the idea of asymptotes, which I had to, as I pointed out earlier, is a little bit different from what you learned in high school. But continuity is the same. However, keep in mind that continuity, although at the beginning it superficially looks like a very simple, basic, intuitive concept, has created some problems for mathematicians. And in the past, mathematicians have had to have a long, hard look at this concept, because it turned out that once a formal, accurate, correct definition of continuity was developed, mathematicians realized that there were several functions that had some discontinuities where we did not expect them, and other functions which had some continuity where in fact we were expecting discontinuities. However, these kind of strange, unusual continuity situations relate to functions that we're not going to be using in the course, so don't worry about them. However, keep in mind that the concept is not, technically is not as simple as it looks at the beginning. So let me start by giving you an informal description of continuity, which pretty much should be very familiar to you. It's the same one that you've seen in high school. In high school, probably you have had it summarized in the idea that a function is continuous if you can draw its graph without lifting the pencil from the paper. Well, this is pretty much what we're going to say. So first of all, we're going to start by saying that a function is continuous at a specific value if its graph has no breaks of any kind at that value. On the other hand, we're going to say that a function is discontinuous at a value if in fact there is some kind of a break, be it a single point hole, a jump, an asymptote, or even some other kinds of breaks that we have not even looked at. More generally, we say that a function is continuous without specifying any values if its graph has no breaks of any kind anywhere. Now, the difficulty with this informal description is that it's not very clear what we mean by a break, and also how do we figure out mathematically if there is a break or not. And that is where the formal description of continuity comes in. And as I said earlier, this description actually is fairly simple. It's not like the formal concept of limit, which is very complicated, especially the formal definition of limit, which we have even skipped. The formal definition of continuity is fairly simple, and it goes like this. A function is continuous at the value x equals c if the following equation is true. So if the limit as x approaches c of our function is equal to the value of the function at c. Remember, when we evaluate a function, we look at the value. When we evaluate the limit, we're looking near the value. If it so happens that the two give us the same conclusion, the same value, then we say that the function is continuous. So for instance, every situation where we have a boring limit would correspond to continuity. However, we're going to see also in class that there are some situations where the limit is not boring at all. In fact, it does deserve to be computed, but in the end it turns out to provide continuity. Now notice that this equation is equivalent to saying three different things. What we're saying with this equation is, number one, that the function exists at that value. So that means that the value c is in fact in the domain of the function. And that's one thing that we need to check. The second thing that we're saying is that the limit as x approaches this value of the function also exists, and that means that it is a unique number that we can identify. And of course, the third thing that the equation says is that those two values are in fact equal. Okay? So this gives us a very clear idea about how to identify the discontinuities. Of course, we don't want to identify the continuities, because for all the functions that we're going to look at are going to be continuous at most of their values. It's going to be the isolated strange number that is going to create some problems. So how are we going to do that? Well, quite simply, we're going to look for potential problem values, the ones where denominators become 0 or something else equally strange happens. Secondly, we're going to check the formal conditions by using limits. So evaluate the function, evaluate the limit, and then we're going to classify each discontinuity depending on what we get as a single point hole, an asymptote, or jump, or whatever.
Now, keep in mind that many books present several so-called continuity laws. These are fairly technical theorems that specify certain conditions under which continuity does or does not occur. they end up being fairly boring to check technically with all the details relating to the formal definition of continuity and limits and so on. But in fact, they tend to be pretty much commonsensical. So just deal with them through common sense. If you want to have a look at those through any kind of reference book that you have, by all means do so. And if they help you, by all means use them. But keep in mind, they basically just say something very similar to the anti-Murphy's law. If nothing is going wrong, nothing is going wrong. So all we have to do now is apply all these ideas to practical situations and looking for discontinuities by using a little bit of investigative work along the lines of the previous 3 points.